Welcome everyone. So I am Aurelian. I'm going to be hosting this session of Flow. So I'm organizing this seminar along with Peter Richterick, Virginia Smith, and Dan Alistair. There is also the very big help of Samuel Horvath here, who handles actually most of the logistics. So thanks again, Samuel. So just for newcomers, maybe, so the goal of this seminar is to provide an online forum to discuss the latest results, scientific results in pretty much all aspects of federated learning, which covers like quite a lot of topics. So this may include distributed optimization, which is going to be, I think, the main topic for today's talk, but also more learning algorithm, the privacy and crypto aspect, personalization, compression for communication, and also the more systems, hardware aspects, and of course, applications. Okay, so today our speaker is Zachary Charles. Thanks a lot for accepting our invite. So Zachary is a machine learning researcher currently working at Google in the context of their AI residency program. He received a PhD in applied math from the University of Wisconsin-Madison in 2017. And after that, he was also a postdoc with Dimitris Papayopoulos. He's working on efficient and robust optimization methods for machine learning and most recently federated learning. He's also an active contributor to TensorFlow Federated. And yeah, today Zachary will present the work on local updates methods, which include many optimization algorithms that are used in the federated learning setting. You can go ahead, or maybe before you start, I will just quickly explain how we take questions, again, for people who maybe haven't attended before. So Zachary is okay to take questions during the talk. So all mics are turned off by default though for the audience. So if you want to ask a question, you can ask it in the chat, or you can use the raise hand feature that you can find in the participants menu. And then Samuel or I can either ask the question for you, or we can essentially turn on your mic so you can ask the question yourself. So feel free to do that throughout the talk. That's it.
Okay, thank you so much for the introduction. Yeah, as Aurelian said, I am going to talk primarily about optimization today. These class of methods called local update methods, and I'll get to what that means. But I do want to point out first that this is really a joint effort directly with Jakub Konechny. But there's a lot of people I have to acknowledge in this work. Valuable discussions were had with most of them. Zachary Garrett at Google, Keith Rush at Google, Brendan at Google, and Brendan had conversations with Nadi, which led to inspiring some of this, and then also Sean Chan at Google. So I want to start off with saying what this talk is not about, because I think that that's a useful framing device. I'm not going to be talking about sharp convergence rates for federated learning algorithms. There will be some convergence rates, but if you want the latest and greatest state of the art, there's a lot of people who are working on this problem, and I highly recommend reading their papers. So Karim Reddy et al., Bayumi et al., Woodworth et al., Yuan et al., many, many others. There's just a lot of great stuff coming out right now on trying to figure out the best possible convergence rates for algorithms like federated averaging. I'm not going to talk about fundamentally new federated learning algorithms. I'm going to talk about old algorithms. If you want to talk about, learn about new algorithms, well, there are lots. There's kind of a lot of different paradigm shifts that have happened. I highly recommend looking at any of these papers. By the way, these slides I have been told will be posted, so hopefully this can serve as a good reference for some people who are interested. I'm not going to talk about application-oriented FL, but I am going to talk about practical FL, and I'll talk about the distinction. But if you want application-oriented FL, there's a lot of great work from Andrew Hard and a bunch of other people at Google. Also, federated learning in healthcare by Brismy et al. In 2018. And I'm not going to talk about compression, privacy, robustness, or fairness. It's a huge swath of work. I'm just not going to address it all. And there's some great surveys by Kairuz et al. And Lee et al. In 2019 that I recommend reading if you're interested. What this talk is about, however, understanding federated optimization in practical settings. So one thing that you might glean from reading federated optimization papers right now is that kind of the state-of-the-art algorithms like FedAverage oftentimes don't do better than mini-batch SGD in theory, or they do comparably to mini-batch SGD in theory. And there's a lot of great work showing that there are cases where it does outperform it, But if you look in practical experiments, federated averaging is frequently better than mini-batch SGD. And so there's kind of a disconnect here as to what's going on in practice and what people are analyzing their theoretical results. And because I'm at Google, I'm more interested in the practical aspects. And so this question kind of keeps me up at night. The other thing that I would like to do is to impart ways of understanding what federated averaging is actually doing. There's so much great work on federated optimization happening right now, but a lot of the papers are very sophisticated. They use extremely sophisticated techniques, and it's not always clear to someone who is not inundated with the latest and greatest in optimization what federated averaging is actually doing from an optimization perspective. And by that I mean, how does it converge? What is it converging to? How does it differ from federated SGD, for instance? And so also the last thing to that end is I am concerned with, well, we understand optimization in the centralized setting to some degree. And a lot of us have intuition for optimization in the centralized setting. And we'd really like to carry it over to the federated learning setting. And it's not always clear what intuition matches and what intuition does not match. The other thing I'm going to be concerned with is learning rates in FL. This is a really, really important topic to me. In particular, what do learning rates mean in FL? And I would argue that they mean something fundamentally different than what they mean in centralized learning. And I'll get to that. The other thing I want to bring up is a distinction between client and server learning rates in FL. And again, I'll talk about that. The last thing that I really have in the back of my mind when I was making these slides is that machine learning in practice is really ad hoc, oftentimes. Federated learning even more so because it's such a new field. And I'd like to help bridge the knowledge gap between theory and implementation. And so how do we make ad hoc learning easier? How do we show people results and experiments that help explain some of the phenomena that they're actually seeing when they say, okay, I'm just going to set these parameters randomly and see what happens. And in particular to that end, if you look at the theory, it's dominated by decaying learning rates and learning rates that are scheduled in certain ways, and you need to make the stochastic gradient variance decrease in such a way in order to get a certain learning rate, whatever. In practice, people don't do that, right? In practice, people first try, I'm going to set my learning rate to 0.1 and I'm going to see what happens. And so I'm very much interested in that paradigm. Okay, so I've said a lot of words. Let's get into like the high level background. This is a seminar on federated learning. I'm going to assume that you're familiar, but if not, here's a really brief introduction. In federated learning, we have this server model. So, and maybe we have a bunch of clients that are mobile phones. We broadcast this machine learning model to the available clients at a given round. The clients perform local training on their own devices. So what that means is that the data never goes back to the server. So this is very much about privacy preserving machine learning. The clients then have their local models, which are now different from the server model. And what they do is they upload it to the server, and the server then updates its model in some way using these local client models. And how it does this update is going to depend on the algorithm. So in particular, the standard algorithm that people use and analyze and understand in this regime is federated averaging by Brendan McMahon and a bunch of other great people. And it's a simple algorithm. It just says, okay, the clients are going to use SGD to update their local models with their local data sets. And the server is just going to average them. Great, done. Then you repeat ad nauseum for however many rounds you want. Okay. So some flavors of federated learning that I think are kind of important to understanding different practical implications of federated learning. There are kind of two regimes that were identified by Kairouz et al. In 2019. There is cross-silo FL. So this is federated learning across large institutions. So for instance, if banks want to collaborate on a model to identify fraud, or hospitals want to collaborate on a model that identifies leukemia in patients. This is kind of an example of cross-silo FL. On the other hand, there's cross-device FL as well. And this is typically FL on edge devices. So For instance, if you want to do next word prediction on mobile phone keyboards, this is a very much a quintessential example of cross-device FL. And I have a table here of some of the distinctions between the characteristics of these two settings. And there's a lot to digest, but the first thing is that just for cross-silo FL, I'm going to focus on a couple of these. The population of clients, so in this case, it would be the institutions like banks or hospitals, it's typically static, right? It's fixed throughout all time. There's not going to be a new hospital that opens up in 3 months and says, we want in on this model. Usually it's fixed. And the distribution of those clients is typically uniform. So we just treat them all as equally participating in this process. And that factors into the optimization as well. If you're doing cross-silo FL, we imagine that typically all the institutions are going to be available at every round because they have quite a lot of compute power. The population size is pretty small, so maybe there are 10 banks that are collaborating. And they're also stateful. This is a really, really important distinction. It means that these clients can actually hold on to variables in memory. They can know what happened to their local model in previous rounds of the federated learning computation, and maybe they can use that to their benefit. So for those of you who are familiar, the scaffold algorithm is a stateful algorithm, and it's very useful. It does a lot of great things because it's stateful, but that's not always the case. The last thing is that cross-silo FL is addressable. The clients are identified. You know which client is which, even if you don't know their data. Cross-device is very different. The populations can change over time. The clients are typically non-uniform. So if I have the latest and greatest smartphone and I live in a country that is fortunate enough to have consistent Wi-Fi and internet, then maybe I'm updating quite often. I'm available, my phone is available to update the model a lot. Whereas if I don't live in a place with consistent Wi-Fi, maybe I'm not going to update the model at all during its training. And this factors in the availability. Only a small fraction of users are generally available at a given time. However, the population size is large. It could be millions or more. And we talk about mobile phones, for instance, you can imagine that you could grow to populations that are billions, right? Like this is a real possibility. However, they're generally not stateful. If I told you, hey, download this app, but it's going to store 50 megabytes of memory just for increasing computation over time, like you might be a little bit dubious. Why does it need this extra memory that it's not telling you what it's doing with? So for general purposes, we assume stateless computation for cross-device FL. And as such, the clients cannot be indexed directly. Okay, so this is a lot to digest, but it's going to factor in later. Another set of introduction that I want to do is meta learning. I'm going to go over this kind of quick. There was a great talk last week in the Flow seminar that I highly recommend reading or listening to about meta learning, but it's essentially learning to learn. It involves learning over a heterogeneous set of tasks. This distribution of tasks is often unknown and difficult to sample from. The thing I want to point out, and this was pointed out in last week's talk, is that you can think of an analogy between meta-learning and federated learning because the tasks are essentially equivalent to clients in federated learning. So instead of learning over a heterogeneous set of clients, we're going to learn over a heterogeneous set of tasks. And you can make this connection more formal. So some algorithms for model-agnostic meta-learning. Just like federated averaging, it utilizes multiple training steps for each client or task. And there's a lot of great results that people have shown equivalence between different model-agnostic meta-learning algorithms like Reptile and federated averaging. Other people have noted a lot of these connections, Kodak et al., Fala et al. So yeah, there's a lot of interplay between meta-learning and federated learning. Okay, so now let's actually get to the setup. Let's define some math. I'm going to be interested in the following setup throughout my talk. The client loss is going to be written as a distribution over the client data. Pretty simple. The global loss is going to be written as a distribution over clients. And the important thing here is that this is going to generalize finite sum optimization. And the moral that I want to convey here is that the finite sum optimization regime of optimization is really more relevant to cross-silo FL. You have a fixed set, finite set of clients. You know which ones are which, and you just proceed in this kind of same way every round. And that's not true for cross-device FL. The distribution of clients can look really, really weird. It can look very non-uniform. And I think it's really worth highlighting that this is a more reasonable, more general setup for cross-device FL. So in particular, we generally have no ability to compute full gradients in cross-device FL. So for instance, SVRG, stochastic variance reduced gradient, whatever, involves a full gradient computation every once in a while, and that's just not possible in cross-device FL. Even computing the global loss is impossible, and I'll talk about that later. Like I said, clients are non-uniform, and another really important thing is that clients are typically sampled at most once during training, right? There are millions of devices and 100 contributed every round. The chances of seeing the same one twice are really, really small. The goal is going to be to minimize the global loss, at least sometimes. So that's going to be our kind of mathematical framework. Okay, and I want to discuss the class of algorithms that was hinted at in the title, local update algorithms. So local update algorithms are going to involve two parts, an outer loop and an inner loop. The outer loop this is the pseudocode for it, and I'm going to go over the important parts. Like federated learning, we start with a server model. We sample some set of M clients. Those clients are going to do some inner loop, and I'll talk about what that means. We average the output of their clients. And then this last step is really, really important. We're not just averaging it and using it as the model. Instead, we're treating this average as an estimate of the population level gradient. And so in particular, there are three really, really important inputs to this algorithm. There is a server learning rate, which I've highlighted in blue, that's used to update the server model. There's also a client learning rate and a client update structure. The client learning rate and the client update structure are used in the inner loop. The client update structure is going to be K real numbers. And what it's going to do is it's going to index a linear combination of gradients. So the clients are going to do SGD on their local data set. So at each iteration, K equals 1 up to capital K, they're going to sample some batch of data from their local distribution. They're going to compute a mini batch gradient. Oh, sorry. They're going to apply SGD. And then the really important thing is that they're going to return some kind of linear combination of the gradients that they computed throughout that training process. Okay, so this is the primary class of methods that I'm going to analyze during this talk. Are there questions about what's going on here? All right, so this is really abstract currently, and let's make it more concrete. There are a lot of special cases of this algorithm, and I'll flip back to the algorithm to help illustrate some of these. But the first one...
sorry, Zachary, we have one question by Tin Duan. Yeah, go ahead, Tin.
Yeah, sorry, just want to clarify the return of algorithm 2. So in algorithm 2, you do a batch update for X, and then the return to the outer loop, it returns the weighted average of the gradient?
Yep. Exactly, exactly.
Oh, okay. So I thought in federated learning, you don't want to transfer or transmit the gradient to the server. You only want to change the iterate.
Yeah, so you can do it. So federated learning is not nailed down. There's a lot of different ways you can do it. And actually, one thing I will talk about on the following slide is that this actually generalizes federated averaging. So in particular, when all the thetas are 1, you're going to actually recover the standard federated averaging algorithm. Because the difference between the server model and the original model is essentially just the sum of the gradients.
So it's okay to transfer the gradient because the gradient depends on the data, right? Is this okay?
This is a really good question. Potentially, yes. Especially in settings where you don't imagine that there are adversarial attackers who are seeing the updates from the clients. And especially you would hope that the server is not adversarial. But if you are in a system where you imagine that there are adversarial actors happening, this might not be privacy preserving. You're right. There are some really interesting works that now reconstruct data based on gradients. And we very much don't think about that in this work. That's a really good point. But it's something to keep in mind.
Thank you.
Yeah.
I would have one extra question. So yeah, in this slide, so you're sending essentially the combination of the gradients. But what we usually see when for other algorithms, that you would usually do some linear combination of the actual iterates. So can you please explain what's the intuition to send rather the gradients than the iterates?
Yeah, that's a really good question. I'll have a slide on this, but the goal here is to entirely decouple the server learning rate and the client learning rate. So over here, we have a server update that involves this server learning rate eta. And over here, we have a client update that involves client learning rate gamma. And for purposes of understanding what's going on, I want these two to have no interaction. So if instead I sent a linear combination of the iterates to the server, there would be this gamma floating around. It would be involved. And I'll talk about why that's an important distinction. Does that help answer your question?
Yes, thank you.
Okay, so some special cases of this algorithm. Distributed SGD, where each client just does one step, is obviously a special case. This is where our theta is just a single one, right? So I have kind of a definition up here, theta k and theta 1 through k. So theta k is just a bunch of zeros and a 1. Theta 1 through k is all ones. If we just have a single thing, you go back to this algorithm, we're just taking a single step and you return that gradient. Easy. Federated SGD uses theta 1 through k. But the important thing with federated SGD is that the client learning rate is 0. You don't actually update the local models. And this gets to what I just answered, why I want to decouple this client learning rate and the server learning rate. I want this client learning rate 0 to be a valid regime for us. I want to generalize both federated SGD and federated averaging simultaneously. Federated averaging is a special case, and it corresponds to the client learning rate equaling the server learning rate, and I'll get to that. The look-ahead optimizer from Zhang et al. Last year is a special case. Reptile, which is a meta-learning algorithm, again, is a special case, theta 1 through k. And then so are some more classical mammal methods. So in particular, faux mammal, which is first order mammal, actually corresponds to theta k. So it's the linear combination is all zeros and then just a 1 at the end. So you just send the last gradient to the server. And the last thing that's kind of interesting, we show this in our work, is that mammal, which involves kind of a Hessian step, if you use quadratic losses, actually corresponds to theta 2k plus 1. So 2k zeros and then a single 1. And I'm not going to talk about the details here so much, but it very much involves the quadratic loss structure. This is not necessarily a general result. Okay, so let's talk about decoupled learning rates, because I think that's really important. The original federated averaging algorithm involves just you update your model as an average of the client models, the local client models. And you do some calculations, I don't want to get into it, but you see that it's equivalent to taking your server model and applying a gradient step with the client learning rate, gamma. So this is in some sense bad. We're constraining the server and the client to use exactly the same learning rate, which doesn't necessarily make sense. There's also a version of federated averaging people have started to use more in practice. It's the so-called model delta version, where instead of sending the average of the iterates, we instead send the difference between the broadcast model and the local model, and we use a server learning rate of eta. And this is a better step towards decoupling, but it's not an entire decoupling, because if you do the math and you do some computation, you'll find that it's equivalent to sending a sum of gradients, but where you multiply eta and gamma. And so both of these disallow the client learning rate of 0, which is a really, really important operating point. And I'll get to that. Okay, questions on this? Okay. So local update methods. Previous work with federated averaging shows that federated averaging may not converge to the minimizer of the loss in heterogeneous settings. And this is a really, really important observation. The observation has been shown many, many times. Lee et al., Karim Moretti et al., Woodworth et al., Malinovsky et al., Pathak et al., and I'm sure there are other people that I'm omitting. But it's this weird issue that federated averaging with constant learning rates is somehow biased. And there's similar findings for mammal and faux mammal. Follow it, I'll talk about this. And I want to analyze this in a more general context of the local update methods. And especially, I'm interested in how the algorithmic choices, especially learning rate, impact this bias of federated averaging. And also, does this matter in practice, right? Is this just a theoretical concern, or is this something that actually happens? And the primary finding, and this is really if you take away one thing from this talk, I want it to be this. It's that in local update, server and client learning rates have different impacts. The server learning rate, you should think of as analogous to the learning rate in centralized learning. It dictates the convergence speed. And it shouldn't be too large, otherwise you're larger than the Lipschitz constant or whatever, but you should think of it as analogous to the centralized learning rate. The client learning rate, and this theta, which governs the linear combination of gradients you send, actually dictates which point you converge towards. So there's really different behavior that the client learning rate and the server learning rate have on your algorithm. Okay, so I want to analyze all this, and I'm going to do it in kind of a restrictive setting. I'm going to analyze it in the quadratic setting. So in the quadratic setting, my client loss is going to look like this. It's going to be quadratic, governed by this matrix AI, and CI is going to be the minima of the ith client loss. So this is 0 exactly when x equals CI. The global loss is going to be the expected value over all the clients of their quadratic loss. What we're going to do, remember, we're interested in how federated averaging may not converge to the true minima of f of x. I'm going to define a surrogate client loss. I'm going to call it f tilde I. And it's parameterized by gamma and theta. Remember that gamma is the client learning rate and theta is the structure that governs the linear combination. And I'm going to define it in a very similar way to the client loss, but it's going to have this now Q matrix. And this Q matrix is going to be a linear combination, the same linear combination of gradients that we send, of I minus gamma AI to the K minus 1. Okay, this definition is going to look pretty weird, but if you write down some equations, it'll make some sense. I won't go into the whole details, but I'll get to why this is really important. And the surrogate global loss, I'm going to just define as a distribution over these surrogate client losses. So again, we have our original client loss and our original population loss, and I define kind of a biased version of them, this version that has a distortion by this matrix Q. And the theorem is that if each AI is invertible, then local update is equivalent to performing SGD on the surrogate loss function. So this is a really, really important viewpoint in my mind. Federated averaging, mammal, faux mammal, all these algorithms are not directly optimizing the true loss function f of x. Instead, they're directly optimizing this surrogate loss function. And the thing about the surrogate loss function is, as people have noted before, sorry, this should be f tilde, but the minimum of f of x is not necessarily the minimum of f tilde x gamma theta. And so this is why you get this behavior that federated averaging does not converge to the true loss function minimizer. Instead, it's optimizing an entirely different function, one that depends on your client learning rate and the linear combination of gradients that you send. And the really nice thing about this approach, and it's why I focused on the quadratic setting, is that intuitive properties of local update can be analyzed by considering SGD on this surrogate loss. So we can take all this intuition that we have from the centralized setting, analyze this surrogate loss, and gain insight into what federated averaging, federated SGD, mammal, faux mammal, all these algorithms are doing. Okay, so these two slides were maybe the two most important in this talk, so I want to pause here for any questions. If not, that's okay. Yeah. water break. Let's say water break. Okay, if there's none, then I'm going to proceed. And I'm going to proceed with an example because sometimes it's really hard to understand these things just from a theoretical point of view. So what we did is we have a very toy example. It's a linear regression problem. It involves, I won't specify the distribution of clients and data, but it's a really simple linear regression example. And we performed federated averaging with k steps. So again, this is you send a linear combination of all the gradients that you computed. And we're going to fix the server learning rate. And we're either going to vary the number of steps or we're going to vary the client learning rate that we use. And what you see is this behavior where if you only use one local step, you do eventually converge to the true minimizer. But as soon as you use multiple local steps, 2, 5, 20, you get further and further away from the true minimizer. And again, this is the surrogate loss in action. When you're doing k equals 20 steps, you're not optimizing the function corresponding to this red line. You're optimizing an entirely different function. You're converging to something else entirely. And you can kind of see from this picture that as k increases, you're really converging to the average of the client minimizer. So you become closer and closer to one-shot averaging. We get a really similar story with client learning rates. When the client learning rate is 0, so the clients are not making any local progress, they're just computing some gradients and sending them back to the server, you very quickly reach the true minimizer. But as the client learning rate increases, you converge to more and more biased things. And the thing that's really interesting here is that there seems to be little to no benefit to using federated averaging. Moreover, if you notice here, when gamma equals 1.0, we're actually worse than one-shot averaging. We're further away from the minima, the true minima, than just if we took the average of all the client minimizers. And this might be kind of surprising at first. Because if you look at this trajectory, this looks pretty smooth. It looks like it's converging. It looks like it's doing something not pathologically bad. But somehow it is pathologically bad. It's worse than the dumbest possible algorithm you could think of for doing federated learning. And what's going on here comes back to this matrix Q and this surrogate client loss function. If gamma is too large, if you look at this matrix Q, it's actually going to be a negative definite matrix. And so what's happening over here is that this gamma is large enough that there's at least one client that has a negative definite loss function. But you can't see that just from the trajectory of the iterates alone. This looks pretty smooth. It looks like it's converging nicely. And so this is kind of an important practical takeaway, is that you have to be careful in federated learning. Your client learning rate has to be set sufficiently small with respect to all clients. The presence of negative definite clients can do bad things to your optimization. Okay, questions on this kind of toy example? All right.
Maybe a quick one. So
yes.
How did you set the data non-IIDness here? Can you maybe discuss a bit the influence of this on those conclusions? So of course, if things are ID, you don't have this problem, but
yeah, this is a great question. So here we do kind of a moderate heterogeneity among clients. It's worth noting that in this example, each client actually only has one data point. So it's just the data points between the clients differ, I think between like 0.5 and 2 or something like that. But you would see this effect become more pronounced as the data gets more heterogeneous. So you would see larger gaps. This is absolutely a great observation. This biased behavior has to do with the heterogeneity of the data.
Thanks.
Yep. Okay. So let's start trying to maybe understand what's going on. And I'm going to make some assumptions for the theory that I'm going to talk about next. The first, remember that we have quadratic loss functions governed by this matrix AI. I'm going to assume that the AIs are positive definite with strong convexity parameter mu, basically, and that our loss functions are going to be Lipschitz with parameter L. So uniformly assuming this. You can relax this assumption to say just the expected value of the AIs has this property, but let's just simplify things for now. And I'm going to assume that my client learning rate isn't too large, so that I'm not doing this negative definite thing that you saw on the previous slide. So one observation that's really important is that the surrogate loss function actually has an increased Lipschitz and strong convexity parameters. So mu and L are the strong convexity and Lipschitz parameters of my original client loss functions. The surrogate loss increases these in ways that you can compute exactly. And because you have this increased Lipschitz constant, this actually allows for a larger server learning rate. And this is kind of an important thing. Larger server learning rates might mean that we're making more progress. So this is one reason that federated learning algorithms might do well initially. The next thing that's really important is that specifically for federated averaging in MAML, not necessarily for all local update methods, but for federated averaging in MAML, even though both the Lipschitz and strong convexity parameters increase with respect to the original loss functions, the condition number decreases. And I have kind of just a short table. So the original condition number, if we're just doing SGD, is L over mu. Whereas if I'm doing federated averaging over here, I get this kind of complicated looking expression. But if you plot it out, you'll see that when gamma equals 0, you actually get back L over mu. But as gamma increases, this actually decreases. For MAML type algorithms, which is kind of governed by theta k, which remember is a bunch of zeros and then 1, this is what the condition number looks like. And it's really clear here that this is smaller than L over mu, right? We have this term that's less than 1. And so this kind of partially explains what's going on with these methods. When you're doing federated averaging, the idea is that we're going to converge faster because we're doing local updates. And we see this in a condition number reduction. Similarly, MAML, it doesn't have the same intuition exactly when it was proposed, but MAML is supposed to be an algorithm that allows clients to take the server model and make quick progress. And this idea of having a reduced condition number plays into this. If your condition number is reduced, you should be able to make progress much faster. Okay, so let's see here. How am I doing on time? 20 minutes. Okay, so I want to say that you can take this theory about this condition numbers, and what we do is we couple it with kind of bounds on the distance between the surrogate loss functions and the true loss functions. So we derive bounds on the distance between optima for general theta. And the expression is kind of complicated. I don't want to get into it, really. I don't think that this is like an important or vital thing to do during this talk, but it essentially has a couple ingredients. The surrogate minimizer, and this is the true minimizer. Their distance is governed by a couple factors. The first is a matter of the data heterogeneity. So in particular, if all the clients have the same minimizer, this is 0. And it's also governed by the surrogate Lipschitz parameter and the surrogate strong convexity parameter, which has a specific form. But you should think of this as just a product. It's heterogeneity times a measure of heterogeneity of optimization. So this LK term is the Lipschitz constant of federated SGD. So the surrogate loss for federated SGD, this is what its Lipschitz constant looks like. And over here is the Lipschitz constant for whatever you're doing. So maybe it's federated averaging, maybe it's federated MAML. So in particular, we can essentially decompose it into data heterogeneity and optimizer heterogeneity. Okay, this is kind of heady and I don't want to get into it too much, but what this allows us to do is actually get some really simple convergence theory for local update. And the idea is that because local update is equivalent to just doing SGD on a central loss function, we can just use standard optimization techniques. No need for complicated analysis. No need for very, very smart techniques that people have developed over the last 5 years. We're going to focus on federated averaging or reptile, kind of whichever one you prefer. It's theta 1 through k. We make a bounded variance assumption, which is pretty standard. And we define some things. X star gamma is going to be the surrogate minimizer corresponding to gamma and theta 1k. Mu gamma is the surrogate strong convexity parameter. And B gamma is going to be the surrogate condition number. And we get a very, very simple theorem that pops out immediately. As long as eta isn't too large, local update satisfies the following bound. The expected value of the t plus first iteration with respect to the biased minima looks like this. There's an exponential decrease factor happening here, and there's this term, which is essentially the noise due to stochastic gradient descent. And this is basically, you can take your favorite optimization textbook, open up Bubek's book or whatever, and this result just pops right out. You know, it's essentially a 2-line proof if you defer to somebody else's work. More complicated, we can ask what happens if we're actually decaying the server learning rate. And I don't want to go too much into this because I think it's not necessarily helpful to gain intuition. But what I want to say is that basically we can decompose our bound into 3 parts. The expected tth iterate minus the actual, the true minima, is going to look like a maximum between beta 1. And beta 1, for those of you familiar with optimization, is going to look really similar to mini batch SGD kind of convergence rates. Beta 2 involves kind of the initial suboptimality. So there's the condition number of the surrogate loss function and the gap between your initial iterate and the surrogate minima. And beta 3 is essentially the distance between the true loss and the surrogate loss. And it's hard to pull apart all of this in an hour-long talk, and especially in just 5 minutes. But I really just want to focus on the consequences because I think that's more important. The first is that the client learning rate should be set according to the desired number of communication rounds. And I think this is a very important factor. In limited communication regimes, when we're not doing very many iterates of federated averaging, we want to increase the client learning rate because back in that previous bound, the initial suboptimality term is really the dominant factor. And what happens with this initial suboptimality is that Fed SGD and mini batch SGD, this term is actually really large. The condition number is large. Whereas for federated averaging in mammal, this term is actually pretty small. So if you think that you're only going to be doing a couple rounds of your federated learning algorithm, you want to be making a lot of progress because of this initial suboptimality. Whereas in less restrictive settings, if you can do lots and lots and lots of rounds, you should be using federated SGD because it's actually going to converge to the true minimum. And this suggests an optimization strategy. We're going to use large client learning rates for some rounds and switch to a smaller learning rate. In fact, you can show, we show this in our paper, in the quadratic case, so 1/t decay is sufficient for both client and server learning rate. Okay, but I'm interested in how we do this in practice. 1/t schedules, for those people who've played around with it, are almost never good in practice. In particular, everything that I've talked about is for quadratic loss functions, which are not useful in practice. So what about non-convex problems? Okay, so I'm going to get to some empirical analysis. That's kind of the complement to the theory that I had. And it's going to hopefully answer some of these questions. And I'm going to focus on federated averaging / reptile and heterogeneous, kind of more realistic problems. And the goal is to understand how the client learning rate impacts the optimization dynamics in non-convex tasks. We saw before in the theory that there's essentially a trade-off. High client learning rates are going to do well initially in optimization of the surrogate loss function, but then level off as you approach this biased minimum. So we run experiments on 4 data sets, and these are publicly available. CIFAR 100, Feminist, Shakespeare, Stack Overflow. And we do 5 different tasks. So CIFAR 100, people might know, this is an image classification data set. We train ResNet 18. And one really important note, we don't use batch norm. Batch norm has weird behavior in federated learning. We instead use something called group norm. So this is image classification. Feminist is a digit recognition data set. It's kind of like a federated version of the MNIST data set. Shakespeare is a natural language processing data set. We do next character prediction with RNNs. And Stack Overflow is this massive data set of Stack Overflow posts. And we perform next word prediction and tag prediction. So tag prediction in particular is going to be convex because it's logistic regression. And so what we're going to do is let's see here. I don't have too much time. I'm not going to talk about this. But we do federated averaging with 10 steps, and we fix the server learning rate first. And here are the results on Feminist, CIFAR 100, and Shakespeare. And the thing that I want to highlight is CIFAR 100 and what's going on here. In particular, I've zoomed it out here. We see that if you set the client learning rate to be 1.0, initially, you just do really badly. You basically make no progress, and this is the surrogate loss in action. You're not optimizing the correct thing. Whereas if we start decreasing the learning rate, we do better and better and better. However, what happens is that this moderate value, this gamma equals 10 to the minus 2, is actually better than the smallest values of gamma initially. So for the first 15,000 rounds or so, this is what you should be using. And then right at the end, 10 to the minus 3 starts to do better because it's actually optimizing something closer to the true loss function. So I think this picture is really important because it confirms that this behavior happens for non-convex problems as well. And again, you see this kind of nice interpolation with respect to the learning rate. Now, one thing that was really important here is that this was a fixed server learning rate. And in some sense, this is a really unfair comparison. Something that I mentioned earlier is that the choice of client learning rate alters the Lipschitz constant of the surrogate loss. And so different client learning rates really should require different server learning rates. Different Lipschitz constants require different learning rates in the centralized setting. And so what we'll have a plot here is with a fixed server learning rate, we plot the update norm for each client learning rate. So this is the L2 norm of the thing actually being used to update our model. And what we see is that when the learning rate is large, we have this really, really small Lipschitz constant. And as gamma decreases, we get actually a larger and larger and larger Lipschitz constant. And actually the variance increases as well. And this makes sense in a lot of ways. But this is just a really important thing to keep in mind, that changing the client learning rate necessitates a change in the server learning rate. The server learning rate you should be using for these large norm updates is different than the server learning rate you should be using down here. So what we do is we actually tune the server learning rate for each client learning rate, and we do a similar comparison. And again, I think the results are worth dwelling on. For feminist, it's a pretty easy task. We see little to no variation between them. But we do see that 10 to the minus 2 does well initially and is eventually outperformed by 10 to the minus 3, just barely. We see a very similar phenomenon on CIFAR 100. But the thing I want to emphasize is that 10 to the minus 2 is now better for longer. Whereas before, for the last 5,000 rounds or so, the smallest learning rates were better. Now we see that 10 to the minus 2 is dominant for almost its entire lifespan. On Shakespeare, this is actually even more pronounced. Whereas in the previous results on Shakespeare, the learning rate, client learning rate of 1.0 was the worst. Once you actually tune the server learning rate, it becomes the best throughout the lifespan of this, throughout the first 5,000 rounds. So despite this suboptimality of federated averaging, in communication limited settings, tuning the server learning rate is sufficient, or sometimes sufficient, to get good behavior. So this is just zooming in. I'm going to skip over this because I've already talked about it. But I also want to emphasize the importance of the decoupling of client server learning rates here. So on the left was the plot we saw before with CIFAR 100. This is with decoupled tuned server learning rate and client learning rate. And on the right is what happens if we fix the original federated averaging algorithm where the client learning rate equals the server learning rate. And we see this really bad behavior, right? Gamma equals 1.0 actually diverges, right? Like it starts to get worse and worse and worse and worse. Whereas it's not great over here, but it's doing something not stupid. Similarly, you don't observe the same behavior where the smallest learning rates actually do well. What's happening is the server learning rate is so small for 10 to the minus 3 that you're just not making any progress. Whereas over here, 10 to the minus 3 actually does do pretty well eventually. So I really want to advocate that you should tune server learning rates and client learning rates separately in FL. It's a really, really important practical point in communication limited settings. And so this is just recapping some of what we talked about. But this suggests kind of a general notion that we should decay the client learning rate over time. We should make fast progress initially, and then we should decay the client learning rate in order to get closer to the true loss. And so we do a pretty simple notion.
Sorry, Zachary.
Yes.
Sorry. We have one question in the chat. So
yes.
It's by Honglin. And the question is, how is the server learning rate tuned? For instance, is it based on the final suboptimality?
The server learning rate is tuned according to the average training loss over the last 100 rounds. Hopefully that answers the question. Yeah. Okay. So I don't have too much time, and I want to get to this algorithm, but basically what we do is we implement a version of decaying the learning rate on plateaus for local update. And this is a pretty standard thing in centralized machine learning. The only thing that's really important here is that it requires more care in cross-device FL because we can only estimate the loss. We can't actually compute the training loss. So in our paper, we have an algorithm, a pretty simple algorithm for actually decaying the learning rate on plateaus, and basically involves estimating the loss function according to the clients. And I don't want to go too much into the details. We have some practical refinements as well. But the thing I want to emphasize is the experimental results. We use our adaptive learning rate decay, this learning rate decay on plateau. And what we do is we no longer tune the client learning rate. Instead, we just take the largest client learning rate that led to non-divergent behavior before. We just say, okay, this is our learning rate. Even if it's a bad client learning rate, we're going to do that. And we're going to use our learning rate decay on plateau technique. And what we find is that in all cases, we actually get kind of dominant behavior, especially feminist and Shakespeare. These methods outperform the others kind of immediately. You get the same fast decay, and then what happens is that because you switch to a smaller learning rate, you actually become a little bit more accurate. The CIFAR results are really cool, and I think it's worth highlighting. We start off with this really bad client learning rate, right? If you look at the trajectory, it's going to do something bad. It's not going to converge. And it realizes what's happening, and it switches. It starts to become much more like the 10 to the minus 2, which is much better. So in particular, we don't see that we're actually doing better here. However, the important thing here is kind of robustness. Even if you didn't do the best possible tuning, you still get comparable results after 10,000 workers. I want to get time to any questions that are left over. So I'm just going to emphasize that we do similar things for the Stack Overflow dataset. But what we do is instead of applying SGD at the server, we can apply an adaptive optimizer. And so we apply the Yogi optimizer, and we see similar results. We combine it with the adaptive learning rate decay, and it does better throughout. And what happens is that here we see similar behavior to CIFAR, where we're initially suboptimal, we decay the learning rate, and we become better than the others. And if you're interested in adaptive optimization federated learning, please tune into this seminar next week, where Sashank is going to talk about some of our work at Google on adaptive federated optimization. So just some really quick takeaways. Decoupling the client and server learning rate is really advantageous. And the client learning rate is not just like a hyperparameter that you tune. It should be set based on the desired number of communication rounds. I think this is really important. And the adaptively decaying the client learning rate can improve accuracy and reduce the need to tune this client learning rate. So some open problems that I want to just mention. Analyzing more general algorithms in this framework. FedProc, Scaffold, and a bunch of others are not actually directly amenable to local update, but I suspect that they can be analyzed in a similar way. And the goal is to really just gain intuition for designing new FL methods. Extensions to non-quadratic functions. Can we view federated averaging as approximating SGD on some central loss in non-convex settings? I don't think that federated averaging is actually optimizing a surrogate loss function, but I think it might be approximating. And last, how do we choose theta, right? This is generally set ad hoc. In my previous experiments, I said theta equals theta 1 through 10, right? I'm going to do 10 steps. But really, what we'd like to do is minimize, with respect to theta, the number of rounds needed to reach a certain accuracy. That would be a really, really great achievement. And finally, how do learning rates and theta impact generalization? I really discussed training error throughout this talk, and generalization is a separate topic that's important. Okay, so with that, I have 2 minutes to spare. So thank you for your time. The full paper is here. The code is all publicly available in TensorFlow Federated here. And please email me if you have questions. Thank you.
Thanks a lot, Zachary. So we can take a few additional questions, and depending on, how many questions there are and how much more time you are willing to stay with us.
Yeah.
So I have maybe one to kick off. So you insisted quite a bit at the beginning of your talk on this distinction between cross-silo and cross-device. So I was wondering a bit if you could discuss a bit the implications of that with respect to what you presented.
Yeah. So a lot of what we talked about, for instance, the method that we used for adaptive learning rate decay, we're kind of putting one hand behind our back, tying one hand behind our back in the cross-silo FL setting. We should be able to do something much better in cross-silo. And I think that there should be focus on utilizing the statefulness and utilizing the addressability of clients to do something much, much better than what's going on here. So if you are interested in cross-silo FL, I would argue use every tool at your disposal and treat it as a separate thing than the cross-device FL case.
Thanks.
I have a question.
Yeah.
So, so you mentioned in open problems several things, and one of the things that I noticed is generalization to non-quadratic functions. So I'm wondering, what do you thought about this work that of Malinowski and Carter's, which tries to do something similar? Of course, there's no really intersection here, but tries to do something similar in spirit, I would say, where instead of thinking of local learning rates, what these people think of is local fixed point operators. So it is known that gradient type methods could be seen as fixed point iterations. So instead of this, one plays with these operators, and then when one does averaging on the master, there is a parameter which can also be thought of as a learning rate. So in some sense, some similar questions are being asked as what you are, but from a very different angle. So would this be going in the direction that you're proposing here as an open problem? What exactly is the open problem?
Yeah, so I will say that work is great. It really clarified a lot of ideas for me. I think that it's one possible extension, this view of fixed point operators. And I think it's a really, really great one because it easily extends past the quadratic functions. The one thing that is difficult there, and I suspect you're probably working on this, is how do you get stochastic methods to work in this framework? And I suspect that this is a non-trivial extension. I suspect it's doable, but it does require some work. But there's also the idea that I don't think that in general, federated averaging can be viewed as a fixed point method. So in general non-convex problems, I suspect that there are settings where the data is such that it isn't a fixed point operator, or you can't.
So, yeah. Sorry. Keep going.
Oh, I was just going to say, so I think there are multiple ways that you can generalize this, and I don't think that there's going to be a single way that works in all cases. I think that's too good to hope for.
Yeah, thank you. So maybe follow up if I may, unless there's some other questions there.
There is one, I guess.
Okay, then I'll ask the follow-up later.
Okay, I have unmuted you, Honglin. I think you can ask a question.
Yeah. So my question is that you mentioned that you have to choose the client learning rates based on the communication round. But there are quantitative formula which links the client learning rate and the communication round.
I don't have one for you. This is part of what's happening here. I would love a formula. That would be really great. And I wish that I had that. But I think it's a really interesting question is how do we actually do that? I suspect that this is unfortunately difficult, right? Even in centralized optimization, people typically don't have formulas for the learning rate that they use. They have ad hoc methods and they have tuning.
I see.
Yeah. It's a good question. It's a very difficult problem, I think.
Yeah.
So maybe I can ask the follow-up question now. So this is not really a question, maybe just a little bit of brainstorming while others come up with questions aloud. So talking about fixed point methods as such. So one of the things that I think about is that, for instance, if you think about scaffold as an algorithm, it's using some sort of a saga-like variance reduction in order to enforce fixed point behavior into the algorithm. Now, what does fixed point behavior mean? One way to think of it is that if you have an algorithm which starts from the optimum, it doesn't go away. So this is the fixed point property. Now, some of these methods, these federated learning methods, do not have this property because they're not designed to be fixed point methods, whether stochastic or not, to begin with. So this variance reduction of the scaffold type is trying to modify the method in order to make it a fixed point method. But now, thinking about these methods which don't have the fixed point property built in, they naturally don't converge. So they converge to something else. And this is something that is related to what you're talking about when you mentioned the master learning rate. So by adjusting this, one adjusts a little bit where does this thing converge to? So so what are your thoughts on this aspect of things? Because I think that methods such as scaffold, they don't belong into this category precisely because they don't do the averaging on the master. They do something smarter in order to make this a fixed point method. And then you get the convergence to the thing that you want to be getting convergence to.
I think this is a really good point. And I think that it speaks to the relative young age of federated learning. I would argue for everybody in this Zoom that federated averaging should not be gospel, right? There are definitely improvements that we can make on it. And one of it is potentially, like Peter suggests, making it more analogous to a fixed point method. And so I think my thoughts on it are, I think the scaffold paper is great. And I think maybe a better question than any of the open problems that I have here is, what are reasonable analogs of scaffold in the cross-device FL version? How do you enforce these kind of fixed point constraints when you have no statefulness on clients? And I think there's a lot of interesting work that people are thinking of in this respect. And smarter people than me, honestly, are designing better methods. And I think that this is really a goal. And I would hope that maybe we can analyze scaffold, FedProx, or other such algorithms in ways that we understand and use that to design these more fixed point-like methods. Yeah. Hopefully that answers your question. I apologize if I'm not 100% on the ball. It is 7 a.m. here. Yeah.
Thank you. Thank you.